Hello friends, welcome to another AI topic video. In today's video, we will be taking something very complex and then we will be breaking it down into smaller components that will make everything easy to understand and also provide examples to make it all have a visual identity in your brain. Let's start with the basics. What is a neural network? Imagine your brain as a big team of tiny workers called neurons. These neurons talk to each other, passing messages to help you think, see, or decide things. A neural network in AI is like a simple copy of that. It's a computer system made of layers of these fake neurons that work together to learn from examples and make smart guesses. To make it feel familiar, think of a neural network like a busy Indian kitchen where chefs prepare a big feast, say for a wedding in a village. The kitchen has different sections, one for chopping veggies, one for mixing spices, and one for cooking. Each section passes the half-done food to the next, adding their touch until the final dish is ready. In a neural network, we have input layer like raw ingredients coming in, hidden layers, the middle chefs tweaking things, and output layer, the finished biryani served. The network learns by trying many times, just like a new cook improves by practicing recipes over and over. Now, to understand how neural networks really work and learn, we need to talk about backpropagation. This is the key trick that helps the network fix its mistakes and get better. Backpropagation is like a smart way of teaching. You check the final result, find out what's wrong, and then go backwards to adjust each part that caused the error. It's called back because the fixes flow from the end back to the start. But to explain backpropagation, let's first break down its main parts one by one, using simple Indian analogies so it's easy to picture. First, weights. Weights are like the amounts of spices you add to a dish. In making masala chai, the weight for tea leaves might be high because they're the main flavor, while sugar is adjusted based on taste. In a neural network, each connection between neurons has a weight, a number that says how important that message is. If the weight is big, the message has a strong effect. If small, it's weak. The network starts with random weights, like a beginner cook guessing spice amounts, and then tweaks them to make the output better. Next, activation function. This is like a gatekeeper in a crowded Mumbai train station who decides if a passenger can board based on how full the train is. The activation function takes the mixed signals from weights and inputs and decides if the neuron should fire or send a strong message forward. A common one is like a simple switch. If the total is above zero, send it on. If not, keep it low. This adds a bit of decision making, preventing everything from being too straightforward, just like how a chef tastes the curry and only adds more chili if it's not spicy enough yet. Then biases. Biases are like the base flavor in your food before you add anything extra. Think of the natural saltiness in rice or the sweetness in milk for kheer. In the network, each neuron has a bias, a starting number that shifts the signal a bit. It helps the neuron activate even if inputs are zero, like having a pinch of salt ready so the dish isn't bland from the start. Without biases, the network might get stuck, like a recipe that always tastes flat no matter what. Now, loss function. This is how we measure mistakes. Imagine you're judging a cricket match score. The loss is the difference between what your team scored and the target. In AI, the loss function calculates how far off the network's guess is from the real answer. For example, if the network is predicting if a photo is a mango or an apple, the loss is high if it says mango, but it's really an apple. A simple loss function is like subtracting the predicted score from the actual one and squaring it to make big errors hurt more. Just like how losing a cricket game by 100 runs feels way worse than by one run. Finally, gradient descent. This is the step-by-step way to fix things. Think of it like climbing down a Himalayan hill to reach a village at the bottom. You don't jump straight down, you take small steps in the steepest direction to avoid falling. In the network, gradient descent uses math to find which way to tweak weights and biases to lower the loss. The gradient is like the slope of the hill, showing the direction of biggest improvement. You adjust a little each time, like a potter shaping clay on a wheel. Turn too fast, it breaks. Go slow, it gets perfect. Putting it all together in backpropagation. During training, you feed data forward through the layers, inputs multiplied by weights plus biases through activation layer by layer to get an output. Then compare it to the truth with the loss function. Now, backpropagate. Start from the loss and go backwards, using gradient descent to calculate how much each weight and bias contributed to the error. Adjust them slightly, repeat with more data, and the network learns. It's like reviewing a Bollywood movie scene. Watch the final cut, spot flaws, then go back to edit the script, acting, and music, and till it's a hit. That covers the core of neural networks and backpropagation. Now let's talk about two types: static backpropagation and recurrent backpropagation. I'll explain what they are, how they're used, and why they fit certain jobs. Static backpropagation is the basic version we just described, used in simple neural networks called feed-forward networks. Static means it handles data that doesn't change over time, like a still photo or a fixed list. The data flows only forward, no loops. Why use it? It's straightforward and fast for tasks where order doesn't matter much. For example, in identifying fruits in a market photo, is this a ripe banana or not? Static backprop trains the network by adjusting weights based on many fruit images. It's used in areas like image recognition, think apps that scan Indian spices in a store, medical diagnosis from x-rays, spotting fractures, or even predicting crop yields from soil data in farming. The reason it's perfect here is because the input is independent. Each photo or data point stands alone, so no need to remember what came before. It's like reading a single page from a book. You don't need the whole story. On the other hand, recurrent backpropagation is a fancier version for networks that handle sequences, like recurrent neural networks, RNNs. Here, recurrent means it loops back, remembering past info. The backpropagation is done through time, unrolling the loop like a long chain to calculate gradients across steps. Imagine it as watching a full cricket match innings, not just one ball. Each ball depends on the score from before. Why use recurrent backpropagation? It's for data where order and time matter, like sentences in a language or stock prices over days. In India, think of predicting monsoon rain patterns. Today's rain affects tomorrow's, so the network remembers history. Usages include language translation, turning Hindi to English, word by word, speech recognition, understanding spoken Tamil with accents building over phrases, music generation, creating a raga melody where notes flow in sequence, or even traffic prediction in Delhi, using past hours data to forecast jams. It's used here because static backprop can't handle dependencies. If you forget the previous word in a sentence, the meaning falls apart, like mixing up a recipe by ignoring the order of adding ingredients. Recurrent version fixes that by propagating errors back through the sequence, making the network learn patterns over time. In short, static is for standalone stuff, quick and simple. Recurrent is for flowing stories, deeper but more powerful for real-world chains. Both build on the same ideas of weights, activations, and gradients, but tailored to the data's shape. With practice, neural networks become like a wise village elder, learning from experiences to give better advice every time.